All right, so in the first graph that you see, let's talk about the idea of symmetry with respect to an axis or the origin. So if you look at this graph here, and first of all, is this a function?
Yes.
Yes, that's a function. And this function, if you really look at it, and I'm going to go ahead and put this transparency right over it, but this function right here, if I were to fold this function about the y-axis, what do you notice about those two pieces? They overlap, okay? So do you see that this graph right here is symmetric about the y-axis, okay? So this graph is symmetric about the y-axis. Most of these you'll be able to tell right away about the symmetry with respect to an axis. So if you fold it, you get this piece. So this graph, and regardless of which side you fold it on, both pieces are symmetric about the y-axis. Now, if I were to say that this was a graph here, would this graph be symmetric about the y-axis? No. All right, so you understand when to tell whether it's symmetric about the y-axis or not. All right, so if you look at it, in order for it to be symmetric about the y-axis, in terms of this parabola, the y-axis has to go through the vertex. See the vertex right here? The y-axis goes through it. So if I move this, if I translate this parabola up 2 units, is it still symmetric about the y-axis? Yes. If I move it down, is it still symmetric about the y-axis? Yes, because if you fold it, both pieces overlap. Okay? But if I move it horizontally at all, is it still symmetric about the y-axis? No. All right, so you understand the idea of symmetry about the y-axis. All right? So this particular graph right here, I'm going to call it right now, I'm going to call this a relation. So remember, relation is a set of ordered pairs. So is this a relation? Yes. This relation, though, is considered a what? Function. All right, so this relation is symmetric about the y-axis. Right, now tell me something about this relation right here. It's symmetric about the y-axis as well. Okay, so if I were to, and I didn't fold it, I didn't have time to fold it, so let me go ahead and fold it now. But if I were to take one part of the graph and reflect it about the y-axis, you will see that I get the other part. See it? And if I translate this relation up, no matter how many units, is it still symmetric about the y-axis? Yes, it's still symmetric about the y-axis. Even down. But if I look at the graph here, is it still symmetric about the y-axis? No. It has symmetry. We're going to talk about symmetry later on, some more. It does have symmetry, but the symmetry is here. See the symmetry? Is that the y-axis? Is this the y-axis? No. In order for it to have symmetry about the y-axis, it has, this vertex has to be on the y-axis. Okay? All right, so this relation is symmetric about the y-axis. All right, now let's look at the next one, next page. And I think, is that the one right here? No, that's not it. It's this one, isn't it? Okay. So tell me something about the symmetry about this relation. It's symmetric about the y-axis as well, isn't it? Okay. So again, if I look at this piece here and I fold it about the y-axis, you get the other piece. See that? So you can tell very easily, if a graph is symmetric about the y-axis. So this relation is symmetric about the y-axis. Okay? And even the next one, right? So this graph is also symmetric about the y-axis, because if I don't think this is it, that's not it, this is it. So if I take this piece here, right here, and fold it along the y-axis, you'll notice you get it overlaps the other side. Okay? So this graph is symmetric about the y-axis. All right. The next one, that's also symmetric about the y-axis, correct?
Yes.
All right. Okay, now we get to this one. Okay. Okay, is this graph symmetric about the y-axis? No, it's not symmetric about the y-axis. All right, is it symmetric about the x-axis? Is it symmetric? No. All right, it's not symmetric about the x-axis, because if I were to fold it about the x-axis, this piece is not here, correct? All right, but it is symmetric about the origin. So let's talk about how is this thing symmetrical about the origin. So let me just go ahead and write this right away. So this is symmetric, this relation, although it's a function, but let's call it relation for right now. This relation is symmetric about the origin. All right, now, when I go back to the one we did earlier, the very first one, and this was, we said this was symmetric about the y-axis, okay? So if I take a point, let's say this point right here, all right, and I reflect it about, and I reflect it about the y-axis, you got to visualize this. I don't have the transparency here. Do you see how I get this point right here? All right, so that point reflected about the y-axis is this point. This point reflected about the y-axis is this point. This point reflected about the y-axis is this point, correct? What can you tell me about these distances from the y-axis? They're equal. So this distance is the same as that distance. This distance is the same as that distance. This distance same as that distance, correct? All right. So that's one of the properties of being having symmetry about the y-axis. Same thing here in the second one. If I look at this point here and reflect it about the y-axis, I get this point. And the distances from the y-axis, from the point to the y-axis, are the same. This distance same as that distance. All right? So a graph is symmetrical about the y-axis is if you can take any point reflected by about the y-axis, it lies on the graph on the other side. And the distances are what? The same. So if we talk about the origin instead, so let's say I take this point right here, this point, and I reflect it about the origin. I reflect it about the origin. So remember we were talking about distances with respect to the y-axis? So let's look at this distance from here to the origin, right here. All right, and then I keep going, that same distance. What do you notice? Right. So when I reflect about the origin, I get this point here, and the distances are what? The same. If I take this point here, okay, that point right here, reflected by the origin, okay, I'm trying to make about the origin, keep going, so I'm reflecting it. What do you notice about these 2 points? This point from the origin is the same distance as from the origin to that point. So do you see that no matter what point I take on this part of the graph, if I reflect it about the origin, I get a point in the other part of the graph, and the distances are the same for each. Okay? So this relation, is symmetric about the origin. And the same thing here. What can you tell me about the symmetry about this relation? Symmetric about the origin as well. So if I take, let's say, this point here, no matter what point I take, and I reflect about the origin. So I'm just looking at these distances right here, and then going the same distance, I get this point here. All right, so those distances should be the same. All right, take this distance here, reflected about the origin, I get that point. All right, so this relation is symmetric about the origin. Okay. Now I think the next one is this one. Is that correct?
Sine function. Yeah.
The one above it, though, right? Okay. So tell me something about symmetry here. What do you think?
It's reflected.
Is it symmetric about the y? First of all, it's symmetric about the y-axis. No. Is it symmetric about the? We haven't talked about the x-axis yet, but you can tell it's not symmetric about the x-axis. Is it symmetric about the origin? Okay. Well, let's see. If I take this point right here, and I reflect it about the origin, I get this point here. Those distances here should be the same, correct? All right. Same thing here. If I take this point up here, and remember this is called a relative max. If I take this relative max here, I better get this relative min then, right? So let's see if I can draw this pretty well. So you reflected about the origin. And you get this point. That's all right. But those distances should be the same. This point here, reflected about the origin. That distance here should be the same as that distance, correct? All right. So this relation is a what? Okay, this relation is symmetric about the origin. All right? Now, next semester, for some of you, you can talk about the sine function. You have to graph the sine function. What do you notice about the sine function? Is this sine function symmetric about the origin, the y-axis?
X-axis.
So if I reflect about the x-axis, I'm going to get a part of the graph down here? No.
Or is that the origin too?
It's at the origin as well. So if I take this point here, reflected about the origin, and remember this is a relative max, which is on test 2. I get this relative min, right? And those distances are the same. If I take this point here, look, this point right here, that's on the x-axis, and I reflected about the origin, look what happens. Make sure you understand this. I get this point here, this other x-intercept, right? That is same as that distance. If I take this point here, this point, reflected about the origin, I should get this point, right? Okay. Right. So this relation is symmetric about the origin. All right, so this relation is symmetric about the origin. All right, so just from looking at the graph, you can tell whether a graph is symmetric about the y-axis, the origin. We haven't done x-axis yet, or neither. So it could have no symmetry about either of those. So remember at the beginning, we looked at this. So we know that this graph, the way it is, it does have symmetry. It's symmetric about the what? The x-axis. I'm sorry, the y-axis, right? Okay, but then I asked you this question. I asked you, if I move it to the right so many units, is it still symmetrical about the y-axis? The answer is no. But it still has symmetry. We're going to talk about symmetry either later this week or Monday. This graph, the parabola, has symmetry. See, if this little crease right here, if I draw a line through here and I fold it, it still overlaps, right? So you're going to learn that this is called the axis of symmetry. So remember this is called a quadratic function, the parabola. All quadratic functions will have an axis of symmetry. It just so happens that here, what is the axis of symmetry? The y-axis. Here is the axis of symmetry, the y-axis. No. But all we're interested in right now is determining whether a graph is symmetric about the y-axis, x-axis, origin, or neither. So if this was a graph I would give you with those 4 conditions, you would say which one? Neither. It is neither symmetric about the x-axis. It is not symmetric about the x-axis. It is not symmetric about the origin. So you say what? Neither. All right? So when you get that worksheet, it will say, is it symmetric about the x-axis, y-axis, origin, or neither? You would say which one? Neither. But it does have symmetry. We just haven't talked about the symmetry if it's not the y-axis. All right? Okay, now, let's look at this for a moment. Suppose I had this. Now look at this carefully. Suppose that my relation looked like this, okay? So if you look at it, you can tell me that this relation, although is this a function? No, that's why we're calling these relations, because almost all of them were functions, but this one is not a function. It fails the vertical line test. But it still has symmetry. Where's the symmetry?
X-axis.
The x-axis. Because if I reflected about the x-axis, see that little crease is still in the x-axis, I get the other part. It overlaps with the other part. And you can still talk about distances. Let me go ahead and kind of draw this. So let's just say I'm just going to draw something. All right, so if I take this point here, reflected about the x-axis, just like we're talking about the y-axis earlier, or the origin, what do you notice about these distances? They're the same. If I take this point here, reflected about the x-axis, these distances should be the same, and so on. Okay? So this relation is symmetric about the x-axis. All right, so that relation is symmetric about the x-axis. All right? Okay, now, we're going to come back, probably not today, but tomorrow, and we're going to actually look at these points, and we're going to talk more about these points. So we're going to look at this point here, compare with this point here, and then in general, talk about what those points look like in relation to each other. So we're going to do that tomorrow. Right now, we're just looking at basically the graph and determining the symmetry. All right, now, let's look at this. Let's talk about even and odd functions. Okay, even and odd functions. Okay, so an even function is a function that is symmetrical about the y-axis. So any function that is symmetrical about the y-axis is also considered an even function. An odd function is a function that is symmetrical about the origin. All right, so an even function is a function symmetrical about the y-axis. An odd function is a function that is symmetrical about the origin. Okay? We can't talk about symmetry about the x-axis because that's no longer a function. We're only talking about functions here now, even versus odd. So if I go back to that parabola we did earlier, well, the very first one. So if I look at the first one we did, what can you tell me about whether this is an even, odd, or neither even or odd?
Even.
It's even. Why is it even?
It's symmetrical about the y-axis.
Because it's symmetrical about the y-axis. So this is an even function. Because it is symmetrical about the y-axis. Now, one of the things you're going to learn when we talk about polynomials is this. If you look at the function, this is f of x equal x squared. And you graphed f of x equal x squared last semester, and you did it on test 1. So that is f of x equal x squared. So for example, if x is 1, what's my y value? What's 1 squared? 1. Isn't that the 0.11 right here? If x is 2, what's my y value? 2 squared? 4. So that is a graph of f of x equal x squared. Now we're talking about polynomials. What do you notice about this exponent? It's even. All right, so x to the second power, x to the fourth power, x to the sixth power, if you were to graph those, they would be symmetrical about the y-axis, and they would be even functions. Okay? So if I were to, I'm going to go ahead and use another grid here. So if I were to look at this, now remember, we said so this right here is what function? Yeah, it's even, but very good. F of x equal what? X squared. Okay, that's f of x equal x squared. If I move it down, if I translate it down 4 units, is it still f of x equal x squared?
Yes.
No, it's f of x equal x squared
Plus or minus whatever.
minus 4. Thank you. All right, minus 4. It's still what kind of function? Yeah, quadratic, but it's still what kind of function? Even. It's still an even function. So if I draw this, and I'm not going to draw it because of the transparency right over it, but it's still an even function. We'll go ahead and write it. That's what this is. What do you notice about the exponent of the variables? The exponent's even. If I move it down, let's say 6 units, this would be f of x, or g, let me call it g of x this time, x squared minus, let me do 7, because I don't want you to think that the constant has to be even. So let's do this one. So this right here is g of x equal x squared minus 7. Is it still an even function? Yes, because it's symmetrical about the y-axis. But what do you notice about the variable, and the only term you see is this one? What do you notice about the exponent? It's even. All right? Okay. Now, let's talk about the second one here. Is this function even, odd, or neither? It's even, because it's symmetrical about the y-axis. All right, because it's symmetrical about the y-axis. All right, now, let's look at this one. Go ahead and look at this one here. Y equal x cubed. We know that it has symmetry. What is its symmetry? The origin. All right, well, a function that has symmetry about the origin is called what kind of function? Odd function. What do you know about the exponent of x? It's odd. And if I were to shift it up or down, if I shift it up or down now, it would still be considered a what? Odd function. See right here? So if I move it up, So this would be x cubed plus 4. That you see, the blue that you see? But it still has, but I'm sorry, let me rephrase it. Does it have symmetry by the origin?
No.
No. Okay? All right, so got to be a little bit careful with that statement. So if I move it up, it no longer has symmetry about the origin, right? Okay. So you really need to be careful with that statement. It only applies with that even function where it has symmetry. You move up or down, it still has symmetry about the y-axis. But moving this up or down no longer has symmetry about the origin. Okay. But x cubed itself, there's no other term there. X cubed itself, the cube, is odd. All right, so kind of remember that for that x cubed, since it's odd, it does have symmetry about the origin. So this would be an odd, this function is an odd function because it is symmetric about the origin. All right, moving up or down is no longer symmetric about the origin. But if I take this right here, move this parabola up or down, it's still symmetric about the what? Y-axis. So it's still considered an even function because that was the definition of an even function. It has to have symmetry about the y-axis. An odd function has to have symmetry about the origin. So if you look at the next one right here, and you can't see it anymore because I wrote all over it, this right here, we saw that this had symmetry about the origin. So this would be considered what kind of function? Odd. Now, it's not function, right? Now look at the variables. Look at the variables. What do you notice about the exponent of the variables? That's x, you can't tell, can you? But look, it's odd because if you look at your own paper, this is x to the third power and the other one is 5x to the first power. All right. Adding a constant to it moves it up or down. It is no longer symmetrical about the origin. Okay? Now let me explain why when you look at this right here, the variables, they're odd, right? I'm sorry, the exponents, they're odd. All right? If I were to move it up or down, let me remind you about something. Can you tell me what 3 to the 0 power is? 1. Okay. So if I were to take this function here that we just were looking at, f of x equal negative x cubed plus 5x. That function itself is even, odd, or neither. It's odd. You can tell from the graph. All right? If I add 4 to it, meaning I'm shifting it up 4 units, just like we did with that x cubed a while ago, it becomes neither. And the reason is because, remember, 4, isn't that the same thing as 4x to the 0 power? What's x to the 0 power? What's 1 times 4? 4. Now tell me, is this 0 an odd number? No. It's what kind of number? Even. Remember, any number that ends in 0 is what kind of number? Even. Okay? So that's why this is not an odd function, because some are odd, some exponents are odd, and some are what? Even. And that goes back to that x cubed we had. When we did that x cubed and I moved it up. The reason it is no longer, when I shifted this up, the reason it was no longer odd was because when I shifted it up, let's say I shifted it up 5 units. How can you write that 5? 5x to the 0 power. Now look at the exponent of the variables. This is odd, this is what? Even. All right, an odd function, if you look at every term, the exponent of the variables must be what? Odd. So you may say, well, 5 doesn't have a variable in it. Yes, you can put a variable in it. You'd have to write it as x to what power? 0. Okay? All right. So we're going to talk more about that as we go through tomorrow. Now, let's look at, let's see, go ahead and take this one out. It's in one of the pages. Do the best you can with finding it. It looks like this. Tell me something about this function. Is this function even, odd, or neither?
Odd,
It's odd. Why is it odd?
symmetrical about the origin.
It's measured by the origin. So if I were to actually write out that function explicitly, all of the variables would have what exponent? Odd. And there would be no constant listed because a constant would be 5x to the 0 power or 6x to the 0 power. It would be all the exponents, every term would have the variable raised to an odd power. All right, but for this, all you really know is that since it is symmetrical about the origin, you can tell it's symmetrical about the origin, it is odd. So this is an odd function. Since it is symmetrical about the origin. Okay? All right, now go ahead and take this one out. It kind of looks like this. Look, find the page that has the parabola that has vertex at -1, and then the other polynomial looks like this. All right, tell me about whether these two graphs are, or these two functions are even, odd, or neither. They're both neither. Okay, good. So this function is neither even or odd, right? This function is neither even or odd. Right? Because in order for it to be even, it has to have what kind of symmetry? Symmetric about the y-axis. In order for it to be odd, it has to have what kind of symmetry? The origin symmetry. Okay? All right, so that takes care of the idea of even or odd functions. Now tomorrow we're going to talk about the specific points, how those points actually related, because that's going to be important as well. So we're going to come back and discuss this a little bit further, but with looking at points. Okay? All right. Now let me just say this, on your in class, I guess we're going to do this because it is on your in class. On your in class, let's go back to that first one. That in class worksheet, that parabola. So here's the way it's going to be stated on that in class worksheet. Let's look at the point. I said I was going to do it tomorrow, but I forgot it is on your in class. So let's just do it now. Tell me what this point is right here. 2, 4. Good. So I'm going to ask you, and this is what kind of function? Even. So if 2, 4 is on the graph of this even function, then what other point better be on that graph? Very good. When you reflect it about the y-axis, you get this point here, which is negative 2, 4. So notice when you reflect it about the x-axis, and we're talking about an even function, the y values stay the same because in it at the same y value level, but the x coordinates are what? Opposites. So this point here, and let's say this is right here. Let's say this point here is 3, 9. So if 3, 9 is on the graph of an even function, then what other point better be on that graph? Negative 3, 9. Okay? Negative 3, 9. So negative 3, 9 better also be on that graph. All right, now let's talk about an odd function. Let me go back to this odd function here. All right, let's do this one. Okay, so remember earlier when I used the ruler and I actually took this point right here and I reflected it about the origin and I got this point? Let's look at those 2 points. Let's do this point here, 1, 1. 1, 1. If I take 1, 1 and I reflect it about the origin, I get what other point? Negative 1, negative 1. All right, so what can you tell me about the x coordinates and the y coordinates? They're opposites. They're opposites. So if you look at, let's say, let's look at this. This was 2, 8. Let's say 2, 8's right here. Okay? And I reflected about the origin. Reflect about the origin. 2, 8. And I didn't do a very good job with it. But what point should this be right here? Negative 2, negative 8. So when you're talking about odd functions, if positive 2, positive 8, if the point 2, 8 is on the graph, then what other point better be on that graph? Negative 2, negative 8. So then, here's another question. If 6, negative 2 is on the graph of an odd function, what other point should be on that graph?
Negative 6, positive 2.
All right, so since this is an odd function, the x coordinates become opposites and the y coordinates become opposites. So the answer is negative 6, positive 2. If 7, negative 3 is on the graph of an even function, then blank should be on the graph as well.
Negative 7, negative 3.
Positive 3, right? Oh, I'm sorry, this is even. I'm sorry, this is even. So it's the y stays the same, so it's negative 7,
Negative 3.
negative 3. So it's even. I was thinking it was still odd. All right? Okay, so you're gonna have that kind of question tonight. So let's go ahead and do it now. Now tomorrow we're gonna talk about the same idea, but with f of x, f of negative x. You're gonna see how that relation comes to play. All right, so that takes care of that part.